The first question in the homework is starting with what's called a recursive function. And these recursive functions mean that you take a previous term and you will do your growth. So you're either going to add or subtract some value. So for this first problem, the initial value is 60. And we add 70. Well, at least for my values, I know this is the numbers change for everybody, but for mine, I have Pn equals Pn minus 1. Those little subscripts, those are just telling you which term you're on. And then you have the growth. So this P0, that means the first or the initial term. And then the next term that you would have is P1. And that just takes the previous term plus the next term, which gives you 130. Whoops, not P2, that's P1. So P1 equals 130. Then to get the second or the next one, P2, you take that previous term and you add 70. And you keep going. Each term is 200. Each term is that previous term plus 70, and so on. Now, after a while, you may say, okay, I don't want to keep adding 70 over and over and over again if I have to get to something like 100. So our recursive functions are taking one term and getting the next one by doing the same operation. So, this term, add something to get the next term, and then add that same thing to get the next term, and keep adding and keep adding. But we can also write what's called the explicit form. And what you do here is you get the explicit term by taking your initial term and then adding 70 however many times, or for whatever term that you're trying to get to. Notice that we have 70 and then another 70, another 70, another 70. So if we do 70 times n, then that's going to give us the explicit version. P100 would be found by, P100 would be found by taking that initial term of 60 and then adding 70 100 times, because that's how many times we would have to add that 70 if we were trying to work all the way to the 100. And your explicit formula will always be that initial value plus whatever our growth is times n, which is whatever index we want, and we'll get our formula. So this one will be 60 plus 7,000. So we have 7,060. Now our next problem is a word problem building on that same idea, where if we currently have 122 lights and the city council is deciding to add 2 at the end of each week for 52 weeks. So they'll stop after a year. And I want to know how many at the end of 48 weeks. So what's happening here? Well, I'm starting with 125, and at the end of the first week, I will have 2 more. And then in the second week, I'll have that 127, and I need to add 2 more. At the end of the third week, we've got that 129, and we're going to add 2 more. So you see here that we're adding 2 every single time. So if we need to go to the 48th week, well, I don't want to just keep adding, and going from 3 all the way to 48. That's going to take too long. So I'm going to use that explicit term again, where we take our initial plus our growth times whatever term that we want. So if I want the 48th, I'm going to take that starting 125. We're growing by 2 each week, and I'm going to multiply that by 48 to get the number of streetlights at the end of the 48th week, because you're going to be adding 2 for 48 weeks. So we have 125, and then that is going to be 96. We add that together, and we have 221 streetlights here. Question 3 is similar, but the way that it's giving us the information, it's not telling us the growth. We have to figure that out. So here in this problem, the first week, so that initial value, we're told that we have sold 4 cars. In the second week, we're told that we sold 6 cars. And we're told that this pattern continues. So the question is, what was our growth? We weren't given the growth, but we can figure it out. If we go from 4 to 6, how much did we add? We added 2. So our growth here is going to be 2. And so if we want to write the recursive function, that's where we base it on that previous term, you're just going to take the previous term and add 2, and that's going to get you the next problem. So whatever the growth is, that recursive, you just take the previous term and add your growth amount. But if you want the explicit form, that's where we take our initial, we add our growth factor times which term we're on. And if I want just the generic one, I'll take my initial value of 4 and add 2 times n, since our growth is 2, and we're going to do that n times. And so if we wanted to figure this out in, say, the 4th week, if I want the 4th week, then I would take just a second. The way this one is worded is actually a little bit weird. The first week was P0. The second week was P1. The way this one was given, so we need to be careful. The 4th week is not going to be P4. The 4th week is going to be P3. If you notice that our index is always 1 less than the week that we're on. So the 3rd week would be P2. The 4th week would be P3. And so we have our initial plus 2 times our growth factor. And that is not supposed to be a 2. We're doing the 3rd week. There we go. All right, P3. So 4 plus 6, and we get 10. On question 4, we are given the initial. We have the 9,000 books, or whatever your number has. And we're going to add 150 each month. So the first question is, write an explicit formula to describe the growth. Now, you do have to pay attention here that this problem has P with a little t. And so our variable is going to need to be t here instead of something else. But we take our initial amount and we're adding 150 each month. So we will multiply by t here. How many are we going to have in a year? Well, what would our t be for 1 year? This one didn't do that weird thing with the numbers. So this one will be P12. Will be 9,000 plus 150 times 12. Now, the third question, this one is one that we haven't encountered yet. This one says, how long will it be before the library contains 18,000 books? So this time we don't know t. But we do know the population. We do know that we want it to equal 18,000. We're starting with 9,000 and we're adding this 150 at a time. But notice here, we plugged in the 18,000 and we're actually going to need to solve for t. So this is where we use our solving these basic linear equations. Subtract the 9,000. so that the numbers are together. And we have 150 times t. To solve for t, we will divide by 150. And let's see, those zeros, I'm doing this without a calculator right now. So 15, that's going to be 6. So we've got 60. It's going to be 60 months for us to get to that 18,000. So it's fine to have a calculator here. I just don't have one with me. All right, so there's question 4. All right, question 5, we are given a formula, 409t plus 5870. And here, t is the number of years. In my problem, it's after 1995. So this is an explicit formula, and if we wanted to figure out in year 2006, well, we need to figure out what our t would equal. And since it's years after 1995, we can find that t by taking the 2006 minus the 1995 to help us figure out how many years we're talking about. So here our time will be 11. So if you're ever measuring years since a certain thing, you just take the current year minus whichever year that you're using as your starting point. And that makes the numbers a lot smaller. 11, a lot easier to deal with than 2006. And so to figure out what the average will be here, you're just going to take the 409, multiply that by the time, which is 11, add the 5,870, and get your answer. Now, if you're using something like Desmos, then you can type this whole thing in. If you're using your cell phone calculator, you need to first do your multiplication and get that number, and then add the 5,870 in 2 separate steps. You can't just type it all in at once on just a basic cell phone calculator because it doesn't do order of operations. Question 6 is a little bit like question 4, so I will leave that one for you to apply. And question 7 is a little bit harder, so let's take a look at that one. In question 7, I have the $300 per person price leads to 250 tickets sold. If they up the price to 500, then they expect to go down to 100 tickets. So if we want to make an equation based on the cost equals some function of tickets sold. So we need to take the tickets sold and connect that back over to our price. We know that when the cost is 300, that we end up with some function that has x. So we'll have some slope with our x of 250 plus some b, some unknown. So you have that multiplying term and then that adding term. All we know is what the x is. So we've got that. And we know that when the price is 500, we have that same m. We sell 100 tickets plus b. So in order to solve a problem like this, there's a couple ways of going about this. But the way I like to do this is we have formulas that actually help us figure out what m equals. So m is going to equal where you subtract the y's, subtract the x's, and divide. So which one's x and which one's y? Well, x is going to be your tickets sold, and then y is going to be your cost. So x is always what the function of is, and then y is always what's over there on the left, what it equals. So we know that for a cost of 500 versus a cost of 300, we will sell 100 tickets versus 250 tickets. These two values have to go together. So 100 tickets, $500, 250 tickets, $300. And so now we can subtract the top, we get 200, subtract the bottom, we get 150 as a negative. The negative is important here. And it just means that we're going down. And we divide 200 divided by 150, and we get negative 4/3. So that gives us our value for m. And so what we can do from here is we can go in here and we can plug it into one of the equations. And use that to solve for b. Now, we do get a weird number here when we multiply. So we get, it's negative 1,000 thirds, or you can get like negative 3 or negative 3.3.3 goes on. We need to solve this. I'm sorry, I ran out of room. We'll solve this by adding that 100 thirds to both sides, or 1,000 thirds, because it's negative there on the right side, and we need to add that. When we solve that, we'll actually get b. And so here our b is going to be, let's see, 1,900 thirds, which will be, I think, 633 and a bunch of threes. So solving a problem like this is pretty tricky. You have to figure out what two numbers go together, how the which one is the function of, which one is the variable, what it equals, and we have to find our slope, and then we need to use one of our two equations that we wrote here to find our intercept. When you do this for question 8, it is very, very similar to this. They call that A and B instead of M and B. So on question 8, you'll do the same thing, figuring out which one is the X values, which ones are the Y values, with your A instead of M. It's just a lettering thing. Question 9, you have the function and you have the x's, so you're just going to plug that one in. Question 10, you're looking at the dots and just wondering, does that look like a line? Does it look like that we should be able to use a line in order to do this? And then we want to try to estimate for a given year in the future, minus 2014. The way this model is given with years, this is common, it's counting years since 1995. So we'll take 2014 minus 1995. We see that we are looking at 19 years, and just plug that into your equation that's given up above. If we want to figure out when this is going to be 347 million, we set up an equation. So we have our equation that was given. And this time we know that we want it to equal 347. What we don't know is what our t is, and we're trying to solve that. So we're solving an equation. We have 17.711, and we subtract that, and you're going to get some number with that calculator. And then whatever number you get, you're going to divide by that 18.997 to solve for t. And question 11 is very similar to this one, so you can use that question to help you through question 11. Question 12 works a little bit different, just the way that it's given your information. We're given the price per hour and the price per parts. So we have $145 per part. We have $40 per hour. So that per hour, that's the multiplication thing. So we know we're going to have to spend $145 no matter what, but we'll spend $40 per hour, and we can let that be a time, or actually, just kidding, that needs to be an X. And I had to look ahead to see that it wanted the X. So here, you take the given amount and then the price per, that tells you that you're going to take that and multiply by however many hours that you have. So that X represents the time spent. The 40, that's going to be the cost per hour. And that 145 is the cost of parts. Then there's a question, how much will the repair cost if the mechanic charges for 4 hours? We would simply plug in 4 into our equation there for X. Question 13 is pretty similar. The only difference is we are draining water. So in question 13, mine starts with having 1,400 initially, but then we're draining, which means we are losing 27 gallons per minute. And so we need to do a minus. But it's very similar. This is the initial amount of water. This is the rate of draining. And the X will be the number of minutes. And then how much water is in the tank after 12 minutes? You can plug in 12 for that. Question 14, it works almost exactly the same. Person is so far away from home, they're driving towards home at an average rate of 47 miles per hour. You just have to think, am I adding 48 miles each hour or am I subtracting 48 miles each hour if I'm heading home? So as you get home, the distance to home is getting smaller, so you would need to subtract to be able to work through that one. But on question 15, you have a certain amount of money and you're adding $53. So setting up very, very similarly, but this time we are adding 53 each time. Now let's take a look at 16. This is a little bit closer to where we were at the beginning of this problem set. So we have an initial population of 8. And we know after 5 weeks, we have 43. But what's a little bit different here is when we're trying to solve our equation, we have our initial plus our growth times our time. This time, we don't know the growth rate. We have to figure out the growth rate. We know, though, when the time is 5 that we're going to get 43. So we start with our initial. We don't know our growth, but we know our time is 5. And we can solve this like any other equation. Subtract 8 from both sides. And you're going to get 35 equals growth times 5. Divide by 5. And here we get that our growth is equal to 7. And so to actually answer this question, we're going to find our PN. I'll pay attention to that little subscript because that's telling you what the variable is. Our initial value of 8, our growth rate was 7, and then our variable N, and that solves the problem. Then the last one, question 17, you're given a table, but it works just like you would in question 16. And it asks, write a model using the first and the last semesters. So we know our initial is at first, and we have 110. We know at the end of the third semester, the value is 173. And so we can find our variable here, and it does have a little t. I want to use t for this one. So our variable will be t. It's just that initial plus our growth times our time. And we don't know growth, but we do know when time is 3 that PT is 170. So we can solve for growth like we did in the last problem with knowing that we have t. Once you get that equation written out, just like we did in the last problem, then you can predict for year 4 by plugging 4 into the equation that you get.